All right, welcome back. Hopefully you had a great lunch, breakfast, dinner. Now we're gonna get back to talk about insulation and moisture control management. So we had a little conflict with scheduling. So what we're gonna do is we're gonna show last offering's video. However, I'll be here live behind the scenes. So if anybody have any questions, you can just chime in. I'll pause the video, address the question, and then we'll continue on. We'll take roughly about 2 hours to get through these lessons, and then you'll be released 1500, hopefully, depending on the questions and everything. But with that, we're gonna watch the videos starting now.
Hey everyone, welcome back from lunch. My name is Captain Joshua Dill. It's a pleasure to be here with you. I am the mechanical instructor here at AFIT. I work alongside Captain Ryan, who some of you may have had in the past. So I'm a mechanical engineer by trade, but I'm going to talk to you a little bit today about where our field overlaps with respect to roofing. So a little bit about myself. Initially, I was stationed at Grand Forks Air Force Base and worked primarily as a project manager there before I was picked up to come here and be the mechanical instructor. Got my advanced degree, my master's degree at Penn State University, and I've been here for about 1.5 years. So we're going to, over the next 2 hours, we're going to talk about insulation first, and then we're going to talk about moisture and mold. So as part of insulation, we're also going to hit energy management as well. And so energy management has been a big concern with the Air Force and the DoD because energy is what enables our missions. And so with infrastructure, we have a piece of that. And we'll let you know which of that is relevant for you and how that relates to roofing. So our goals for the next hour here really are to comprehend how kind of heat transfer works, what are the characteristics of insulation that define its performance, and how does that relate to the heating and cooling that we have to provide within that building. So a lot of this lesson is really just exposing you to various types of insulation. Now there are a plethora of different insulation types out there. I'm going to really focus on the more common just to get you introduced to them. If you're on there with your, if you got Wi-Fi where you are or your smartphone, it's really helpful just to Google images, Google different pictures of these installations to give you more of a feel for them. And then we'll talk about the energy management program and what specifically guidance on roofing installations there is with respect to that. So, all right, so the first thing, a little bit of understanding of my field, HVAC, and the building envelope. Certainly weather is really going to drive a big portion of how much energy we have to send into this facility. In the summertime, that energy is going to come into our roof or through the solar gains that we have. In the winter, in the nighttime, we're losing energy out of our facility. And so all of this, these arrows, that heat transfer, that's what I'm primarily concerned with as a mechanical engineer. And our goal is to limit that. So we do cool roofs, we do reflective roofs in order to limit that heat gain. And we really try to, bulk up our insulation in order to keep that energy inside. So there's a number of factors here. Insulation is a big one. The other big one is the thermal mass of our facility. Now that's a term that you may or may not have heard of before. So let me just wake you guys up initially coming back here. Maybe I'll shoot this one out to Spangdalam there. Spangdalam, what do we mean when we say thermal mass? What are we talking about? How does that impact our heat transfer?
AFIT, this is Barksdale.
Barksdale, thanks for coming to the rescue. Please.
There it absorbs or it holds the heat or holds the coolness in.
Has to do with the ability of a material to retain heat.
I think I had a few of those. So I heard retain heat. Can you say the beginning of that again? Barksdale.
Thermal mass is the ability of a material to retain heat.
Yeah, exactly. Very good. The ability to retain heat. Spangdam, I see you coming in here on Adobe Connect. Appreciate it. So certainly, I think retaining heat, that's a good way of putting it. So if you think, for instance, of a parking garage or a roof that's made primarily of concrete, it takes a long time for that to heat up. That's why in the evening you might walk across a parking lot barefoot or a road, and even though it's cool outside, the ground is still hot because there's so much heat that's been stored in there. In the same way, a facility that is being pounded by the sun during the day, it's going to take a long time for all that concrete to heat up. So that's going to play a factor as well. So the point here is that it's not just insulation that affects how much heat transfer we have, but also thermal mass. You know, my house, I got masonry, I got brick. That's going to impact it a lot. But for the most part, most of our homes are made of just, you know, wood studs with insulation. There's not a whole lot of thermal mass there. It doesn't take a long time to heat that up or cool it down. So heat transfer is really going to be driven more so by the insulation than it would in, you know, our beautiful Air Force facilities that are all made of a lot of thermal mass most of the time. So, what type of roof we have, if we have a metal roof, if we have a concrete roof, that's going to impact it as well. So there's more things at play here than just insulation, but insulation is definitely a big one. And obviously weather is the biggest factor. You know, just like gravitational potential energy, you know, the more height that you have, the bigger potential energy you have. In the same way, the more temperature difference you have, the bigger thermal energy that you have. And so, you know, our climate regions that are extremely cold, it's going to be a lot more important to control our heat transfer than it is in some of these more temperate climates. You know, where it's not going to be as big of an energy factor. And so, and we're going to talk about that's going to come into play as well when we talk about moisture control and mold. So these will have different requirements based upon what region you're in. So what I'm going to talk about here with respect to insulation really comes from the whole building design guide. And so we harp this quite a bit, and that's because there's a lot of good information on there. So if you go to the whole building design guide and the roofing systems, they talk about all the insulation that we are going to spend the next 45 minutes or so talking about, as well as some of these other materials. And so even after this course, as you want a refresher, you know, go back and check out some of these references. I certainly find it helpful because there's, even just preparing for this, I go back and refresh myself on the different types of insulations they have and the different characteristics. So to start off, when we talk about insulation, I think we all understand, hey, it's a blanket for your facility. You're trying to slow down how much heat transfer. And it really is the biggest factor. You know, we obviously have to construct our facilities to hold up the roof, you know, to provide shelter from the elements. But without insulation, we're just going to be bleeding energy. It's going to be cost prohibitive. So there's a variety of locations that we can place our insulation. The big way we define insulation is either by thermal conductivity or thermal resistance. Now these two are related to one another. For the most part, we define insulation by R value. So thermal resistance is how much we resist the heat transfer. And so this is given to you for a specific thickness. Thermal conductivity is kind of the opposite. So thermal resistance, the higher R value we have, if we have R11 insulation, that's going to be better than R4 insulation. The higher resistance, the more we're resisting, the better energy transfer, the better characteristics to prevent energy transfer. Thermal conductivity, on the other hand, is how well do I conduct heat. So, for instance, things like metal, they have a high thermal conductivity, a high K value. So these two are kind of inverse of one another. The main other difference is that the K value is given per length. So if you don't know how thick your insulation is, the K value would be more beneficial to you. So, but for the most part, we're going to be talking with respect to thermal resistance. That's how we define our insulation. Now, thermal energy, For those that are not mechanical engineers, the unit that we use is the BTU, the British Thermal Unit. It's one of these, made-up English terms that makes sense intuitively, but doesn't really appear a whole lot outside of mechanical engineering. And a BTU, 1 BTU is just the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So you'll see that unit quite a bit. And the locations that we don't use it is where we're going to have more heat transfer. So we can place it obviously within our walls, our stud walls.
All right, did you have audio
in our
again,
crawl
please?
spaces, because we're
Confirm
going
it.
to have heat transfer with respect to our foundation. That concrete is going to transfer heat, and that's going to go
right,
out
got it,
of our
thanks.
facility. And then the one we're going to talk about quite a bit is how we use it in our roofing systems. And so you can do it one of two ways. At your house, like my house, and I imagine most of yours, you have just a flat insulation, typically non-rigid insulation that you just lay into your attic space. But if you have a built-out attic, you may have insulation along the deck there in a pitched assembly. And so it really can be done either way, and we'll see different examples of this. But this is typically where we are installing it if you had X-ray vision where you could look through the building materials. So this is one of the slides that probably of most value is, hey, we can install this in 3 different kind of assemblies. And really what drives this is the type of roof that we have. So for instance, we can install that in the first option there below the roof deck in a pitched roof setting. And so this was in that case where you have an attic where it's a living space. That's how you would install this. Or even, I suppose, it's below the roof deck in a typical configuration where it's just laid on the top. So in this case, you're going to want to ventilate that space between the roof deck and the insulation. So the attic at my home, I'm going to want to ventilate this because it's going to cause, a lot of heat to be, stored in there, and that can cause issues of condensation, which we'll take a look at. The other option, that second option, is we can install it between our roof deck and our roofing membrane. So, very common in a, built-up roof type scenario. So, in this case, we're going to have, light insulating concrete fill or rigid foam. So a lot of times we're going to use rigid foam in these applications just because it can stand the heat with some sort of cover board, which we'll talk about. And the last one is less common, but we can actually install that over the roofing membrane. So if we have a roof where we're going to have traffic, in a terrace or something like that, you want to protect that membrane from the occupants walking all over it. And so the insulation over the top of it, this inverted roof, allows us to accomplish that. The key here is you're going to need a very specific insulation that can withstand the moisture that it's going to be exposed to, the elements, that sort of thing. Otherwise, as insulation predominantly gets wet, you're going to have derated capacity, derated value, and so that's something to consider as well. So typically we're going to use XPS insulation in an inverted roof, which we'll talk about here. So just a couple examples here. Very similar to probably what you have in your house, flexible, non-rigid insulation below the roof deck. Between that membrane and the roof deck here, that's where we install our insulation. And then typically what we do is we install some sort of cover board material here, which allows us to protect the insulation, but also to fasten that membrane to the actual insulation. So typically probably what you've seen the most. And then in an inverted roof, we have our deck here, we have our membrane right here, this black strip, and then we have our XPS insulation, which we'll talk about here. You'll know what that means. And then, of course, maybe some stone ballast just to allow our occupants to walk over and without having to damage it. So that's kind of the broad overarching where we can install it, let's talk about specifically the specifications, the things that we're looking at. And so in the next few slides here, the next several slides, there's a lot of words on here which I'll try to hit the highlights, and a lot of them are for your reference going forward. I talked about the R value. The R value is really probably the most important factor with respect to how that installation is going to perform, because ultimately that's what we're paying for. We're paying for how well you're going to resist the heat transfer. But there's other factors that we need to consider. For instance, if this is a flat roof, you're going to have foot traffic, and so compressive strength is going to be important. You can't just have a flexible insulation installed in a built-up roof where you're going to be walking all over it. You need to have compressive strength and rigid insulation up there. How well does it respond to heat? If we're using hot bitumen or adhesives, it needs to respond to heat a little bit. And obviously, cost and some of these other factors are going to weigh in significantly as well. So those are some of the metrics, the specifications that you'll see when you look at insulation, and we'll talk more about. Okay, so what I want to do here is go through different types of insulation just to give you some examples. And so primarily we're going to look at rigid versus non-rigid and just a few different examples. So let me see here. And then, there's that other type of, so typically rigid board we're going to use in low slope, as I talked about, because we're going to have foot traffic. Rigid board gives us the compressive strength that we really need. Non-rigid for your homes and your attic spaces. And then we got kind of this in-between that kind of doesn't really fall, the sprayed polyethylene foam, which is, it's very useful with respect to locations that are hard to get, but it's kind of more of a special application there. And so these are all the different materials that we might use based upon different types of insulation. So there's, all insulation really is gathering these different materials from the environment and constructing them in such a way that they don't take heat transfer real well. So fiberglass we're all familiar with. Perlite, as we'll see, is essentially crushed up volcanic rock. Some of these more polyethylene, these kind of chemically developed, that's really what defines and distinguishes insulation types from one another. So, all right, so let's look at our rigid type of insulation here before we get on to the non-rigid form. So there's three primary types, and there's more than these, but rather than just list every single one here, let's give you the most common, let's get you familiar with those, and then as you're out there in the field, look up more that you might be using in specific applications. So, polyisocyanate foam board. That's the first and last time I'm ever going to say that in this lesson, because typically we're just going to refer to it as ISO board, and this is, by far our most common rigid insulation that we use. The other two types that you'll see quite a bit are expanded polyester and extruded polyester, XPS and EPS. So same material, just the way they manufacture it's a little bit different. Now we also have materials that are classified as insulation, but they're really used more so as cover boards, as kind of a transition from the insulation, which you don't want to poke a bunch of holes in your insulation, because then you're getting rid of the air voids, you're creating a thermal bridge where heat can transfer. And so we use cover boards quite a bit that have R values that are useful to us, but that's not your core insulation in your facility. So perlite and wood fiber board is commonly what we use there. And then a lot of times you might see a composite board, which is really just a combination of these two, two layers laminated together. Typically, a lot of times you're going to see ISO board or EPS in a composite board, and then one of these types of cover board materials. So let's take a look at some examples. And I try to highlight in blue here the big takeaways from these different insulation types. And so, again, low slope roof, we're going to want to use ISO board, rigid insulation where it has a strong compressive strength, as well as compatible with those hot temperatures that we're using to create our membrane for our roof. So ISO board is has a high R value per unit thickness. So we don't have to use as much of it. We're talking about decreasing the actual thickness of our roof, but not sacrificing that R value, which is really what we're paying for. It's also cheaper than the extruded polyester there, and again, that cover board is really what you're going to want in order to actually mechanically fasten this in a way that's useful to you. So ISO board is very common, typically used in our built-up roof scenarios. The other one that we have is expanded polystyrene, EPS. So that first bullet there is probably the easiest to actually remember this. This is very similar to styrofoam. Great when we encapsulate it in concrete. Typically what we're going to use that for. That is probably the insulation of choice when you're going to, encapsulate an insulation with concrete. Not so common with ISO board. And then our R values are going to remain relatively straightforward over time. Not a whole lot of threat to, it's not going to absorb moisture like other insulations would and derate the capacity. So it holds up a little bit better for that. But again, it's not great for high temperatures, and so you're going to need a cover board in order to protect you from that. All right, the last one. Sorry, I try and get pictures in here for you guys, and that forces me off screen here. But XPS, this is the one that is the best with respect to withstanding moisture. So this is the insulation that we're going to use in that third option where we are actually installing our insulation over the membrane. This is by far and away, it's just not going to absorb moisture like some of the others are. Which is kind of what I'm saying there in that third bullet there. So, but the problem is, compared to ISO board, you're going to have to pay more for that additional feature as well. So, let me transition here to some of our cover boards, which are, they're classified as insulations. They do provide R values. I talked about that volcanic rock that we're essentially, crushing up. These are thin pieces. We can install them right on the cover board and make it kind of a combined, insulation type, or we can purchase them separately. So low R value, but high resistance to temperatures, better than our insulation on its own. So coupling these together is what allows us to get the benefit, but also get the constructability, coupling the perlite insulation with like an ISO board, for instance. So we talked about encapsulating concrete. Reminder, we don't use the lightweight insulating concrete for, our facilities anymore, but there are some that are out there, and it's good to be familiar with what industry does as well. So, combining these two where we form our concrete around that insulation. If we look at a facility that has, a membrane that's kind of sacrificed here, we're getting some ponding. Maybe this insulation's been exposed to the elements, and we've lost some of its capability. You look in the white here, we have that EPS type insulation, which we're trying to install over the top, and we can use it in a tapered form like this, get that low slope, get that water off of our roof, and add that new membrane in there. So this is something that you see fairly often as well. And then I talked about the composite board as well, using an ISO board in conjunction with a perlite or wood fiberboard type of insulation. So, and this you can nail into, whereas you wouldn't want to nail in straight to the insulation. So I don't know how well this one comes through. Maybe those on Adobe Connect, it's a little bit difficult to read these. But this is a good summary of, the different types of insulation we talked about. What are their R values? You can see that ISO board has an R value of 6 for every inch. So very beneficial with respect to keeping the heat in, as well as extruded polyester. So this is going to, but we also said isoboard's a little bit cheaper. So this is going to give us the most bang for our buck. And then you look at the, we can get up to 100 PSI XPS insulation. That's very good for those inverted roof scenarios. And so some of these other insulation types that are compressive strength as well. So these are probably the two most important factors, certainly not the only, but some of the most important is that R value and the compressive strength of that insulation that we're going to use within our facility. So before I go on to to non-rigid insulation, any questions on rigid board insulation? I know it's for the most part just kind of show and tell here, but again, I encourage you guys to Google some of these images on your own time as well. So some of our non-rigid insulation, this is more common what you see at your home, probably more familiar with it. Glass fiber, mineral wool, really just changing the type of material that we're using there. Very common is that fiberglass, which we're all familiar with. And this guy right here, anybody know what we have our insulation in yellow there, and then we got this piece of paper here, but we only have it on one side. Anybody know what that is? If you go down to Home Depot, you get yourself some R11 flexible insulation. What's that piece of paper on that, taped to that, or stapled?
Vapor barrier.
That's correct. I don't know if you guys talked about it. That's the vapor barrier that you've just connected right on there. We're not going to want it on two sides because that's going to cause problems for us. It's going to trap moisture in there. And we're going to talk about that. How do you install this in the next hour? But where your climate location is, I'll give you a little teaser here. Where your climate location is going to vary whether or not you install this on the outside or the inside of your facility. So here's some of the ones that we talked about. Semi-rigid rock wool on the bottom left there, and loose cellulose fiber. For the most part, almost crushed up newspapers or blankets. Mineral roll insulation here. So not as common in maybe your house applications, but you do see these on occasion as well. So the other thing we can add in addition to a vapor barrier right on that insulation is a reflective insulation panel. So we talked about before that sun beating down. As temperatures get hot, they are going to energy is going to travel through radiation as well. So if you think of your oven, the way an oven works is I make the surrounding oven all very hot. I have a cold turkey ham or whatever it is that's in there, and energy radiates between the two. It's not heating up the air, which is then heating up the oven. If that were the case, you'd have what's called a convective oven. If you don't have a convection oven, you essentially just have two temperature differences and electromagnetic waves. Same way in a microwave. Okay? So one of the ways we could reduce radiation heat transfer, in an oven we want that, in our house we don't necessarily want that, is we can install these, essentially a aluminum foil, this reflective surface, which is going to, as the temperature difference, as radiation travels and hits this, it's going to be reflective off rather than absorb. And so that's going to also decrease our heat transfer and give us some benefits to installing this and give us not extra R value, but also reduce the total heat transfer into our facility. So again, for those on Adobe Connect, I apologize. Hopefully you have the slides and you're working through these. It's a little difficult to see here, but what this is showing is that apparent thermal conductivity on the y-axis here. So I talked very briefly at the beginning about thermal conductivity, but the higher thermal conductivity is, the more heat transfer we have. So metal has a very high thermal conductivity. The lower it is, the less heat transfer we have. And then we also have the density of that insulation as well. Some of it, flexible insulation, maybe we could pack in tighter. For the most part, rigid insulation, you're going to get what you get, right? And so what you'll see here, some of our better, our rigid insulation, polyethylene here, polyurethane, this is a very low K value. That's a rigid type of insulation. That's what we're looking for there. XPS as well, that's another example. And then some of these others as well, where if we can get flexible insulation, so this is glass A fiber, this big, ski jump or half pipe, whatever you want to call it here, as we pack that insulation more densely, to a certain extent, we're going to get a lower K value. Now, there are limiting returns here, and everything over here, you're just paying more for more material, but you're actually not getting any beneficial heat transfer out of. So, part of, purchasing and installing this insulation is trying to hit this sweet spot with the flexible insulation. Not so much a concern with rigid insulation because there's not a whole lot of variance there. So that's just another characteristic of the insulation that you may want to be aware of. Now, while you want to get the certain density, what you don't want to do is you don't want to squish or compress that insulation. Part of that you might not be able to get away from when you're installing insulation at your house because that insulation's got to fit in your wood, your stud wall there. And so you might have to push it in a little bit, but what we don't want to do is crush that insulation, just shove it all in there, because now you're essentially wasting your money, and I'll show you why that is. So here we have graphs of different types of R insulation. We have the thickness reduction, and we have the thermal resistance, that R value. That's what we're paying for, okay? So let's say I took R19 insulation here, this last graph, this last line here. So when I don't reduce it at all, it's right at 19. Well, that makes sense. That's R19 insulation. Same with R14, R11 insulation, and so on. But if I were to crush R19 insulation or smush it to essentially 50% or half its actual value, that's this x-axis right here, what do I get? Well, I'm actually getting around R12 or R11 insulation if I do that. So, when this insulation becomes compressed, we lose some of the value that we've paid for it. If that's the case, we might as well have paid R11 insulation. It would have been cheaper. And so something to be aware of if you're seeing contractors, excessively, smush insulation in order to fit it within the requirements or the constructability space. You do want to take care of this stuff and not just walk all over it on the job site or whatever the case may be. Okay, so going back to our first example where we are installing it over the roof deck, constructability becomes kind of a challenge there, between or over the framing member. So you can see here, our deck kind of purlins here, where we're laying the insulation in between there. This is where it gets challenging, because if all we do is lay it in between here, you have this, what we call a thermal bridge. If you think about, how electricity or how water likes to flow, everything's going to follow the path of least resistance, okay? Water running down the road, as a kid, you always kind of throw stuff in there to try to stop the flow of water. Well, water is going to divert around it because it's easier to go around it rather than try to go over the top of it. Same with electricity. That's why we ground in our facilities, so that when we have a surge of electricity, that electricity goes through the low resistance in the ground rather than through the socket and into my body. So the same way here, if I just have an exposed kind of, metal or wood, stud I am going to essentially, energy is going to follow the path of least resistance. It's a lot easier to go through that than it is to go through the insulation, and so I lose some of the energy there. So we want to cover up those as well, but constructability is a challenge, but there are solutions to that. So, for instance, as you can kind of see here, this gets sloppy and difficult to do. You're either going to crush the insulation and lose the value, or you're even going to knock the insulation that's serving you well here as you're trying to get it in there. So, what happens if we don't have good insulation there? Well, you get a scenario like this where you can clearly tell in a northern tier base where heat is transferring out of. You can see right along where those uninsulated purlins are, and that's what's melting the snow there. So there's actually a pretty good video here done by a manufacturer about one of the ways that they've developed and to get around that. So let me go ahead and play that here.
Welcome to our instructional video on the installation of the new Sealed and Safe system. We are proud to show how easily and efficiently this new system installs. We specially designed each thermal block in 6-foot length, which is the standard width of 2 roof sheet panels and also the typical width of a metal building insulation roll, making the thermal block lengths easy to handle and most accommodating. Each thermal block comes with 2 flathead screws to hold the 6-foot thermal block in place. When installing the thermal blocks, there needs to be an inch overlap on each side of the purlin to meet the energy codes. Each thermal block needs to be butted up to each other. Consider the placement of the flathead screws through the thermal block so that the sealed and safe fasteners are not in conflict with the flathead screws. Thermal blocks are placed over the tops of the purlins and are attached by 2 flathead screws. You can either screw the first flathead screw at the end and the second screw around 12 inches from the first, or you can screw the flathead screw at each end. The Sealed and Safe fastener has been specifically designed to be used with the Sealed and Safe thermal block system. Use of the fastener is mandatory as it is key to the performance of the Sealed and Safe thermal block system. The 6 amp 2500 RPM electric screw gun will be needed with a depth locating nosepiece. Most screw guns run at a higher RPM and will need to be adjusted so that the drill head of the screw functions properly. Once the insulation blanket and the roof sheets are placed over the thermal block, Sealed and Safe fasteners are screwed through the roof sheet, insulation, and thermal block into the purlin below. The design of the fastener creates a stitch-type joint between the roof sheet and the thermal blocks, creating a watertight seal while fastening the whole assembly tightly to the purlin. The fastening process is very much like a typical screw-down roof. The only additional step is to set the thermal block in place with the 2 flathead screws and the use of the Sealed and Safe fasteners.
Well, I apologize for the quality of that video, but hopefully you could see kind of what they were doing, installing what they call that thermal spacer along the purlins there. So, you're going to have a gap if you don't have that. And so what they're advocating and what they've come up with is that thermal spacer, which allows you to fasten that roof deck, but also provides some of the R value that we're ultimately looking for in order to reduce that total heat transfer. So this is kind of what they publish as the benefits of using that thermal spacer and how that will impact your actual total savings here. So the idea of using it with that screw down roof versus just using a typical insulation, this is really capturing that thermal bridging where energy is going to follow the path of least resistance here. So they're claiming they can get 56% of the savings by implementing those thermal spacers there. So you always take that with a grain of salt when the contractor gives it to you, but nonetheless, it makes sense that you're going to get some savings as well. So this is just kind of a summary of the different R values, if you will, and benefits of some of this different insulation that we had. We talked about perlite extensively. the cellular glass, shown down here, not as high of an R value. It's not as bad as perlite though. And then these are, this is the batting cleanup in our roster here. These are the heavy hitters that we typically go with, that you're typically going to see in low slope roofs, and then in a pitched roof setting, you're going to see a non-rigid or flexible insulation installed. And so isoboard that's where we're going to get the most for our money. But XPS is definitely what you're going to want to use in an inverted roof there. And then the last one, that sprayed polyethylene, we don't necessarily classify that as a rigid or a non-rigid. It kind of falls in between. Maybe easy and attractive to use from that standpoint, but compare this insulation, 3.6 per inch versus 5.6 per inch. This is not going to give you as much of heat resistance, but I know at least once at Grand Forks, we had an issue where the control tower, there was thermal bridging going on there. The facility's already been built. You can't rebuild the roof, and that's when these are a good application to come in there and spray that underlay, the underside of the deck there in order to prevent some of the heat transfer that's going on. So now what I want to talk about is just give you folks a little bit of perspective on the major energy policies that have been implemented and why and how installation and those codes are driven by some of these policies. So it really goes back, kind of in the modern era of energy management, if you will. The EPA Act of 2005 was the biggest one, which got us rolling. Everyone understands we need to save energy. But this was the first major legislation since the 1992 EPA Act. Prior to that, quite frankly, we didn't really care a whole lot about how much energy we consumed. It just wasn't necessarily a concern. Certainly things like the oil embargo, they cause us to have a little bit more awareness of it, but this is what got it going in the modern era. So kind of the big highlights from here was we want to reduce our energy intensity by 20% by 2015. So last year we got those 2015 results. I'll show you kind of how we did there. But this was all off of a 2003 baseline. So between the 12 years between 2003 and 2015, we wanted to reduce by 20%. It also directed that federal buildings had to be designed 30% better than ASHRAE standard 90.1. Now, let me explain what ASHRAE standard 90.1 is. So ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. What they do is they do studies, they put out guidance and recommendations. And so this is one of their standards, 90.1, which we'll see, which is the standard for low, non-residential, low-rise commercial facilities, essentially. And so this basically says, we recommend that every building that's constructed consume less than this standard facility, per square footage or whatever it is they're looking at. And local codes and local states will choose to adopt or choose not to adopt. So for instance, California, which is a very aggressive, energy-saving state, will say, well, we want you to go even further than this. But ASHRAE standard 90.1 is a very common standard that a lot of states adopt and say, yes, buildings that are built in our state, they need to abide by standard 90.1. The federal government said 30% better than standard 90.1. Okay. So the other thing is, in 2007, this is under the President Bush administration, issued an executive order which said, you know what? We want to up our goal of energy intensity reduction to 30% by 2015. So he said, let's do better than the law. Let's go with 30%. So, and there was also some reduced water and some other things in here, but we're not going to talk about those. So, but in 2007, an executive order doesn't carry the full weight of law, and so the next big policy was the Energy Independence and Security Act, of 2007. So this really gave the weight of law to that executive order. And so it said that all new facilities, have to reduce their fossil fuel generated energy by 100% by 2030. So essentially what the DoD and the federal government are saying, we want to go net zero by 2030 for all new facilities, new construction. That's an aggressive goal, and there's still a lot to be done to actually make that. The next big policy was under the, moving into the President Obama administration here, upping again, initially it was 20% energy by 2015, and then they upped it in this executive order. We want to go 7.5% total between 2015 and 2020. So now we want 37.5% total energy reduction by 2020. So roughly a third of what we were using per square foot as we did in 2003. And then the last executive order in 2015 was again upping that now we're going to take a 2015 baseline, and we want to go 2.5% per year through 2025. So you're talking about 25% of energy reduction between 2015 and 2025. So the common theme here is more aggressive. Let's reduce our total energy consumption, and there's a lot of reasons for that. When I hear this, it's very easy to be skeptical and say, this is just not realistic. We're going too far, that sort of. But really the goal here is, at the end of the day, the Air Force doesn't necessarily, as a CE officer, I hate saying this, we don't necessarily care about is infrastructure as much. Like, we need infrastructure that enables the mission, but what we care about is, putting warheads on foreheads, if you will. Our goal is, we need energy to allow aircraft to carry out the mission. Now, you got to have facilities, you got to have all those other things to make that happen. But every additional energy we put into facilities is less energy that we can put into mission and aircraft. And so that's one big piece of it. There's all sorts of geopolitical and economical factors that are driving this as well. But at the end of the day, and the other aspect is, the more energy we consume, if we lose, if we want to back up that, if we want to move toward generating our own energy in a microgrid and looking at resiliency, things like that, it's going to be a lot easier to do that if our energy usage is lower than it is higher. So what I always advocate to everyone is, start off going and figuring out how much do you pay for electricity and thermal energy. How much do you pay for your natural gas? How much do you pay for your energy per kilowatt hour? So I've gotten myself down to 400 kilowatt hours a month. That's what I typically use. And I want to see if there's anyone out there that can beat me. So shoot me an email and let me know if you can consume less energy than that. All right, how did we actually do? Well, from our 2015 metrics, these, I didn't talk about all these goals. These were some of the goals that we had. Our goal for energy intensity was 30%. That's the main one I talked about. In 2015, we didn't get there. We only got 24.3%. Well, that's still reducing our total energy by a quarter. I mean, that would be equivalent to right now getting rid of 1/4 of all of our buildings. I mean, that's a lot of energy. And so while we didn't meet our goal, I mean, they also kind of changed the goalpost on us, right? We went from 20% to 30% in those two acts. But so something to be proud of. Renewable energy. This is one that's growing. A lot's changed in the renewable energy if you haven't been following. Solar and wind have gotten a whole lot cheaper, and this is only going to continue to grow. But this is where we were at 2015. 6% of our total goal is 7.5%. And then the last one was water intensity. Our reduction was, we crushed it in water. Our goal was 16. We reduced by almost a quarter there. So water was the easiest one, apparently. So next time you're washing your hands and you don't have enough water because they installed one of those low flow, at least you can say, well, at least the Air Force has made their water intensity goals. I can be happy about that. So all of those laws and regulations, they were all kind of enforced on us, if you will, by this guy right here, the Unified Facility Criteria 1-200-02 is the high performance and sustainable building requirements. And so this has recently changed, and we have a whole course dedicated to talking about what's in that UFC and what is required. But for new construction and major renovations, we need to be 30% better than standard ASHRAE 90.1. So that's really kind of the goalpost for us. And so I talked about what ASHRAE standard 90.1 was. It's, you know, that standard for buildings except for low-rise residential. And so this gives a variety of things based upon climate zones. It gives the maximum U values. It gives minimum R values for insulation. And you know, this is an example of kind of what that table looks like here. So what you're looking at is non-residential and residential. What are the minimum values for insulation? So let's just look at roofs, because that's what we're talking about in this class. If we talk a metal building here, a non-residential metal building, that minimum R value has got to be 19. So, you know, this is, I don't have access to 2013. This is actually an older version of ASHRAE 90.1. But just like the rest of just like the federal government, ASHRAE 90.1 is constantly moving the goalpost on their, you know, this has probably gone up to 20, I would guess somewhere in the 20s. But this is an example of some of the codes that the contractors that are constructing our facilities are going to be required to meet. And, you know, it varies by the climate region here. So for instance, climate zones 1 to 3, they require, ASHRAE 90.1 requires a cool roof or some sort of solar reflectance. So, so what are climate zones 1 through 3? Well, that's in this pink, you know, red and orange area here. So pink is just way down here in the southern tip of Florida, red and orange here. These are all areas where you have a lot of solar energy. Closer to the equator, you have more sunlight there. They require a cool roof, or you got to have higher R values. You got to have a R33 if you're above the roof deck, and R35 at the metal for metal roofs. All right, just last slide here before we put you guys on a break and go on to moisture. You know, what is the max, you know, what is the best thickness I should have for my money? What you're going to see here is on the y-axis here, I have cost per year. On the x-axis, I have how thick that insulation is. So if I buy more and more insulation, the initial cost to actually install that is going to go up. Relatively linear because it's sold on a per foot basis, right? Now I'm going, you know, the benefit of that is I'm going to reduce how much heat transfer I have. You know, this half pipe or this ski jump graph here. That's going to lower how much heating or cooling I need to provide into my facility. And so there's a sweet spot here where, you know, we want to save energy and we want to be green, but we also care about the green that's in our wallet as well. And so, you know, this kind of inflection point here represents the minimum cost where buying additional insulation, yes, you get reduced heat transfer, but you're not gonna save your money. You're not gonna make your money back. So there's a limit to this as well. You know, don't go buy yourself 20, you know, 2 or 3. I don't even know how thick home insulation would be. You know, you got to fit it within your wood studs anyway. But point being here is there's a trade-off there. So with that, folks, I've covered kind of what I want to, which is kind of expose you to different types of insulation. Again, Google those. You know, go out to the job site, see what type of insulation they're using within the roofing projects you have going on. Energy management, that is just going to become more and more of a concern. At the end of the day, the Air Force is about airplanes and not about infrastructure. So we're going to be the ones that have to conserve energy, even though the pilots and the aircraft are consuming a whole lot more of it. So that's all I have for you guys. Some additional references as well as in addition to the whole building design guide. I'll put you guys on a break, but before I let you go, any questions out there with respect to,
All right, welcome back. Well, no, welcome back. You should be watching, right? Does anybody have any questions about this lesson before I put you on break? All right, so what we're going to do is we're going to take a 10-minute break. We'll come back and we'll finish up with the moisture and control lesson. And that one, I'm actually going to stop at some point to explain something that I want to make sure everybody gets. But hopefully this lesson was valuable, and let me know any feedback.